Okay, I think the time for you lectures come. Please, Professor Holger Kersten, Institute for Experimental Vintage Physics, Germany. Please introduce title of your presentation.
Yeah. Yeah, thank you very much, Victor, for this kind introduction. Dear colleagues, ladies and gentlemen, I hope you can understand and see the transparencies. I'm really very glad, and I have to thank the organizers for this kind invitation to the EFRE Congress 2020 in Tomsk. And I would really like to come to Tomsk, to Siberia, but as you know, it's not possible. So this is a video conference, and I thank also the organizers for this perfect organization of the technical issues here, so that it works with the transparencies and with the video link and with the connection. Thank you very much. The title of my talk is Energy and Momentum Fluxes in Plasma Processing. And here my co-workers, Thomas Trottenberg, Alex Spätmann, Mathis Klette, and Luca Hansen are listed. Thomas, he is an assistant professor in my group, and he is an assistant researcher, and Mathis and Luca are PhD students in my group. Maybe you may ask, where is Tomsk is Kiel. Kiel is in the north of Germany, at the Baltic Sea, near the Danish border. So somewhere here is Berlin, here is Kiel, and it is directly located at the Baltic Sea, and especially in summer, it is a very nice region for sailing. You can go sailing here, and this is a photo of our city. Here is a so-called Förde. This is a fjord. Here's the Baltic Sea. Here's the fjord. And our university is located here somewhere in that region of Kiel. And if you once have the chance or to come to Kiel, I would really recommend to do that in summer, because it's really nice sailing region here at the Baltic Sea. Okay. The outline of my presentation is, after a short introduction and motivation of the talk, I will just discuss what we call non-conventional plasma diagnostics for the determination of the energy flux from a plasma to a surface by so-called colorimetric probes or thermal probes. And then I will discuss shortly the measurements or plasma diagnostics of momentum transfer between plasma and surfaces, and especially for an example of sputtering. I will show it for sputtering, and we used recently an interferometric probe, interferometric force probe for these measurements, and I will finish with a short summary. Okay, let's start with the introduction. On the one hand side, we have our plasma, our process plasma, which is very complex by itself. And as you know, you can influence the plasma by macroscopic knobs, for instance, by the gas flow or by the gas pressure or by the excitation frequency of the discharge or by the supplied power, the gas mixture, the composition of the process gases, and maybe also by the geometry of the electrodes and something on. And by these macroscopic knobs, at the end, you will get a plasma with internal parameters, which are determined by the electron energy distribution function or the ion energy distribution function, and finally by the densities of the charge carriers, the electrons, the ions, by the, if you have molecular gases, the degree of dissociation, degree of excitation, and of course by the energies, by the typical energies of the species. In a case of a Maxwellian distribution, we call it the temperature, of course. This is on the one hand side. On the other side, you have the surface, the solid surface, a substrate or an electrode or a wall. And also this system, the wall, is very complex, the solid surface. It can also be influenced by macroscopic quantities, like you can have an additional potential, a bias potential, positive or negative. You can heat or cool the solid substrate. You change the temperature. There might be also the geometry. Is this a 2D or a 3D substrate? Is it amorphous or crystalline, or is it an oxide or a metal, and so on? So it is very complex, the surface, and also there a lot of elementary processes occur, like adsorption, desorption, chemical reactions, sputtering, and so on. And now you bring together these both complex systems, the plasma and the substrate or the solid. And as you know, if you bring them together, there is a sheath in between. There is a sheath between the plasma, the quasi-neutral bulk plasma, and the solid. And through this sheath, energy is transported and momentum, and there is a strong electric field. And you want to know as much as possible about these systems, so you need diagnostics. And there exists, of course, a broad variety of many diagnostics, as you know all. For instance, for the plasma, Langer probes for the electrons, or retarding field analyzer, or Faraday cups for the ions. There might be self-excited electron resonance spectroscopy. This is an active electron spectroscopy. Of course, optical spectroscopy in emission or absorption, or as laser-induced fluorescence, or quantum cascade laser absorption spectroscopy. There might be photometry, there might be mass spectrometry, or even energy-resolved mass spectrometry, which is called plasma monitoring. There might be current voltage probes, and during this conference, we have heard already a lot of different interesting talks about these different diagnostics or microwave diagnostics. All these diagnostics are available, and we use them also. But as you know, in the sheath, it is often very complicated to get information about the sheath. You can measure in the quasi-neutral bulk plasma, but it is only very few methods to get information about the sheath. And we introduced, or we use, what we call non-conventional diagnostics, energy flux measurements and force measurements, and also sometimes we use microscopic dust particles, small microparticles, as probes. But I will speak today about the energy flux measurements and the force probe measurements. And also from the view of the distribution function, the velocity distribution function of the involved species, this is an important issue. Because, you know, if you have the first moment, or let's say the zero moment of the velocity distribution function here for electrons or ions, and if you integrate over this velocity distribution function, of course, you know, you get the current, the flux of the charged particles. If you have the first moment, then you have to integrate over the velocity distribution function with the square of the velocity, of course, and you get a force, or it means a momentum flux. Of course, there might be additional forces. For instance, in addition to the forces by the particles, there might be forces due to the electric field in the sheath or in front of substrates. And the second moment, if you have the second moment over the velocity distribution function here, then you get the power. And that means it's an energy flux, the energy per time. Here is the momentum per time, it's a force, and here it's the energy per time, it's the power. It's the power flux to the surface. This is by the particles, by the charged particles, but again, there might be other contributions to the power balance at the surface. For instance, if you have radiation from the plasma or other sources, you can have maybe condensation energy by growing films, by deposition of thin films, by chemical reactions, and so on. And the question is, can you measure these power flux, these energy influx from the plasma to the surface? And I want to remind you, or to give a motivation why it is interesting. This is the so-called Thornton model of deposition of thin films, but this model was originally introduced by Russian colleagues, by Movshan and Dervishin, already in 69, and later Thornton, he improved this model, and recently, a few years ago, Andre Anders in Leipzig, he modified this model again. And what is important, if you deposit thin films, you can see here is the temperature of the substrate or the surface in units of the melting temperature. So 1 means it's the melting temperature, and here it's 20% of the melting temperature. And of course, if you heat your substrate during the deposition of the thin film, you can influence the morphology. So you can go from amorphous to microcrystalline to crystalline structures of your thin film. That you can do. But sometimes, for instance, for plastic materials or polymer materials, you cannot heat it to a very high temperature. So, but you want to have also at low temperature, maybe even at room temperature, this crystalline structures. And you can do another thing. You can insert or introduce or inject energy by ions, for instance, by ion bombardment. If you decrease the pressure or if you increase the ion bombardment, you can change the morphology of the growing film even at low temperatures or at lower temperatures. So this is interesting. This is just a motivation why the energy influx should be measured or should be determined for thin film deposition. Another example is many years we were working in so-called dusty plasmas, in modification of small particles, of micrometer-sized particles in a plasma. And of course, such a particle is a substrate in the plasma, a floating substrate. And at the surface of these particles, a lot of processes can occur. There might be energy influx by the ions or by the electrons, depending on the potential of the particle, but there might be also irradiation of the particle, there might be losses by radiation, there might be in molecular gases association of atoms to molecules, so the molecules are formed at the surface. This is also important for interstellar clouds, for the dust in the interstellar medium. There might be chemical reactions with the dust particle surface, and of course there might be recombination of ions and electrons. And all these processes contribute to the energy balance of this particle. And at the end, you have an equilibrium temperature of the particle as a result of the different fluxes of the incoming and outgoing energy fluxes. So you can determine this energy balance, and you can tailor the energy balance of such particles. And another example, we did some measurements with Australian colleagues together for growing of small columnar carbon pillars, as you can see here. It are not carbon tubes, nanotubes, but are pillars, small carbon pillars. And that was in methane and hydrogen plasma in argon. And in order to grow these pillars, you need footprints, you need a catalyst, and they deposited a very thin nickel layer, a few nanometers, and then they have to be structured, this nickel layer, so that at these points, at the nickel dots, the columns can grow. the carbonaceous columns. And of course, you can structure these nickel dots by an ion beam or photolithographic process, but you can just do that by the temperature. If you change the energy flux to this surface, you can melt these small thin film, and you can get such structures for the growing pillars. And if you do so, you just can heat, or you can change the temperature or energy balance of this surface just by playing with the gas. As you can see here, here's just by changing the pressure, here's the argon, the pure argon plasma, and here is the argon and hydrogen plasma. And at the same conditions, the same power and the same pressure, we have here almost a double energy influx. And that means we heat up the surface for this structuring of the nickel layer. And why is this the case? This is due to the hydrogen. The hydrogen is dissociated in the plasma, and the hydrogen atoms, they recombine at the surface of this nickel layer and heat the surface by this recombination or by this molecule formation. And so you have different energy influxes and different temperatures. And so you can structure here this very thin nickel film to these nickel dots where you can grow the pillars. Okay, as I already mentioned, this energy influx, or the power which is deposited at the surface, or the power balance which is influenced by different contributions. For instance, you have gain and you have loss processes at the surface. Gain processes might be irradiation by the plasma itself, depending on the energy of the plasma, by surrounding walls, they might be heated, or even by sources. For instance, if you have an electron beam evaporation, then you have a very hot crucible, which is a heat source for your substrate. There might be kinetic energy of the charge carriers, of the electrons and ions. This contribution depends on the bias voltage, of course. For a positive bias voltage, you will attract more electrons, and for a negative, you will attract more ions. There might be kinetic energy of neutrals. For instance, in sputtering, the sputtered neutrals, they carry a certain energy from the collision cascade in sputtering, and these kinetic energy can be transferred to the substrate, to the growing film. There might be heat of adsorption and condensation during the growing film. There might be exothermic chemical reactions at the surface, which heat the substrate. And there might be, of course, recombination of charge carriers and of atoms, here neutralization and here molecule formation. And then energy is released, and this energy heats your surface, your substrate. And of course, there can be external heating. If you have a heater by infrared or by an electro-ohmic heater, for instance, you can heat your substrate. On the other hand, you have losses, again, radiation to the environment of the substrate, and this is mainly infrared radiation. There might be also heat conduction and convection along the substrate holder and along the gas. There might be desorption into the gas phase. There might be endothermic chemical reactions. There might be sputtering of particles and secondary electron emission, and of course, external cooling. So all these contributions, they cool the surface. Here they heat the surface and they cool the surface. And at the end, you are in an equilibrium process where you have a equilibrium surface temperature due to these different processes, due to these different contributions. And the question is, can you measure this energy flux? That means how many watt per square centimeter are coming to the surface from the plasma. And there exist different methods. One is the measurement, you just measure the spatial gradient of the temperature. For instance, if you have some thermocouples along the substrate holder or along the substrate, then you can measure the temperature at the different locations. and or positions, and you can get the dt to dx, so that's the spatial gradient. And from that, if you have a calibrated power, if you know the spatial gradient, you can determine the energy influx. What we mainly use is the temporal slope. We measure the heating and the cooling of the substrate during the plasma process. That is what we call passive thermal probe. This is a passive thermal probe. We just measure heating and cooling of the substrate. But you can also do that actively, that we call an active thermal probe. For instance, you heat your probe to a certain temperature, and if you get an additional energy flux from the plasma, then you need less power to heat your probe because there is an additional power flux from the plasma. And so you can measure the jump in the power as a number for the incoming power from the plasma. I will show you an example. And you can use tiny particles, microparticles, for instance, where you can measure the equilibrium temperature, as I already explained. Okay, and why is the energy influx so important? I give you already a few examples, but I'd like to cite here a sentence by Noah Hershkovitz, who wrote, "Plasma processing characteristics are similar when only a limited number of plasma parameters are identical at the plasma wafer sheath boundary. Identical values of energy flux and particle concentration result in identical rates." So that means if you know the energy influx from the plasma to the surface, you can compare different plasma processes. You can compare different reactors with each other in order to optimize the process for industry or for technological applications. And at the end, as I mentioned, during this plasma surface interaction at low pressure plasmas, you have the energy of the impinging particles. This is the energy transfer, and you have also the momentum transfer by the particle flux. And at the end, it results in the surface temperature or the equilibrium temperature. And this temperature influences again the different elementary processes at the surface, as I mentioned in the beginning. For instance, it is influenced by the temperature, the adsorption, the diffusion, the desorption of the species at the surface, the chemical reactions, the composition and stoichiometry of the growing film, and also the structure, the crystal orientation, the morphology, and so on. So it is really interconnected, these quantities. And as I mentioned, you measure, or there is an integral energy influx from the plasma to the surface, but this energy influx consists of different contributions, as I already mentioned. And if you can try to measure this integral energy influx, I call it here Q in. This is just the integral over the surface area of the substrate or over the probe of the flux density, of the energy flux density. And this energy flux density, which is an integral value, consists also, what I mentioned, of kinetic energy, of electrons, of ions, of neutrals, of condensation energy, of recombination energy, of radiation energy, and so on. And you can try now to identify each of these values by an equation. For instance, for the condensation, the heat of condensation depends, of course, on the deposition rate and on the density of the growing film and the specific energy of condensation of this material, if it is a copper film or aluminum film or whatever. Or if you look about the kinetic energy of the electrons or ions, for the electrons, you just use the Boltzmann factor and, of course, the energy of the electrons. And for the ions, you use the Bohm flux and the bias voltage, which influences the energy of the the ions, of course. This is just an example, or for the neutralization, if there's recombination of electrons and ions at the surface, you of course need the ion energy and the work function for this material, because it's neutralization. So you can try to address all these processes by a formula, by an equation, and compare these theoretical sum of the contributions with your measured sum of the integral energy flux. And as I mentioned, we have two methods. One is the active thermal probe, and I just want to shortly mention how it works. As you can see here, this is the probe, and you can insert the probe by a feed-through to your reactor, to your plasma, and it's very simple. You have to heat this sensor area. For instance, here it is heated to a certain temperature. I go to the next slide, better. Here you can see we heat, in this example, our probe to a temperature of about 340 centigrade, here, the red line, and we need for this temperature a heating power of our sensor of about 600 milliwatt. Okay, and now we switch on our source, our plasma source, or in this case it was an ion beam source, and then in order to attain the same temperature, we just need much less heating power, here only about 50 milliwatt now, because there is additional energy influx by the ion beam or by the plasma. And that means this jump in the power, in the heating power of the sensor, is the power which is coming from the source, from the plasma or from the ion beam source. So you can directly measure by this jump. Here in this case is an influx of about 500 or 550 milliwatt by this example. And this was, for instance, tested in a setup for electric propulsion tests. So we had here a stage that was a project with the European Space Agency, and we had here the ion beam source, a thruster, and a lot of different diagnostics. And one of these diagnostics is here the active thermal probe. So we could measure the beam profile of the ion beam, as you can see here by this method, for different operation regimes. I will not go into detail, but you can measure here the integral energy flux by this very simple method. But mostly we use what I call the passive thermal probe, and this is even more simple. You just have to switch on your plasma, and then the temperature increases, and if you switch off the plasma, the temperature decreases. If you cannot switch on and switch off the plasma, then we use a shutter, for instance. So we open our probe and we close our probe, and then we get the same curve, of course. Here you can see this is the probe here. This is a kind of a dummy substrate which we insert into the plasma, and we measure the energy flux here to this substrate. And then it's very simple. It's like textbook in the first year for the students. You just have the heating of the probe and the cooling of the probe. And this is related to the time derivatives of the temperature during the heating phase and the cooling phase. You just have to have the derivatives here. Usually we take it here in the beginning of the process. And if you know the heat capacity of the probe, you have to know the heat capacity by calibration procedure. Then by this simple formula, you get the integral energy flux. You get the integral energy flux measured by this probe. It's really very, very simple. And here we have different evaluation methods. We have a software and hardware to make it automatically the measurements here from the beginning. And usually we evaluate the so-called heating kinks here when the heating starts, and here the cooling kinks when the cooling starts, which can be measured automatically. And then the power per area can be determined. And at the end, we get a value like 5 watt per square centimeter, but this, I remind you, is an integral energy influx, which has to be, which is the sum of all these different contributions. As I mentioned, to know the heat capacity of this probe, of this thermal probe, we have to calibrate this, and we are doing this in a high vacuum chamber just by an heated wire. So we emit an electron beam, and there are no collisions on the way. And so we know that by the current and the voltage of this electron beam, which hits the probe, the probe is heated, and this is measured, and so we can calibrate the heat capacity of our probe, as you can see here. So this is important to get absolute values of the energy influx. And we tested, or we used this simple thermal probe at different environments, plasma environments. I will show you a few examples. One example is in high-PIMS sputtering. In your congress, you discussed also a lot of these things of the high-PIMS sputtering. You know the difference between high-PIMS and DC magnetron sputtering is that you just have the whole discharge power in a very or rather short pulse of the discharge. That means you have very high power density at the target, at the magnetron target for a short time. And so you have a lot of sputtering of the metallic species, and also a very high degree of ionization of these sputtered species. So the ionization of the sputtered material is much, much higher than in the DC sputtering. Yeah, so we have power densities in a DC sputtering of a few or 100 watts per square centimeter, and here we have kilowatt per square centimeter. And in such a high-PIMS magnetron device, we measured also with our thermal probe. This is again, you see here a spectrum for the titanium target in DC magnetron and high-PIMS magnetron, and you can see here much, much more pronounced ion lines, titanium ion lines in such a high-PIMS spectrum. You can just even see if you look by your eyes in the discharge chamber. This is here the magnetron. It was a 2-inch magnetron in copper, a copper target in an argon discharge. And here on the left-hand side, it is a DC discharge, and on the right-hand side, it's a high-PIMS discharge here at 500 hertz and 40 microsecond pulses. And you can even see by the color. Here, this is a typical argon glow, the argon plasma, and here the green color shows you that there's much higher copper intensity, so it's excited copper, and the copper the copper ion lines and copper excited lines are much, much more than in this case. You can just see it's at the same pressure and at the same power. Yeah, so but you have here a much higher metallic sputtering part. So, and then as you can see here, our thermal probe, we move the thermal probe radially, axially, and angularly in order to map, here's the thermal probe, in order to map the energy flux or power density for deposition of thin films. And these influences, of course, the grain structure. For instance, here's a grain structure of a deposited metal film for DC magnetron, and here for high-PIMS magnetron. So, for instance, the grains are much larger in the high-PIMS case than in the DC case. So we have here a radial distribution. This is the high-PIMS, the energy flux here at substrate position for the high-PIMS case and for the DC case. And you may be astonished that the energy influx in the DC is higher, but that's not a surprise, because here we have a continuous plasma, a continuous sputtering in the DC case, and here we have a pulsed sputtering, as you know, in the high PIMS case, and the plasma is here only for a short time. That means and we measure an average energy influx, an average power deposition, and the average power deposition is even lower in the high PIMS case than in the DC case. And this is interesting also for deposition of thin films for polymer materials or for thermally sensitive materials. So, and then we map here the area, as you can see here, and here is near the target. It's very inhomogeneous, as you would expect, but here about axial position of about 10 centimeter from the target. It is a very homogeneous area of the energy influx here, and that means it's also a very homogeneous deposition here. So the substrates for thin film growth in this high PIMS process should be situated, should be positioned somewhere here. And also as you know, due to the pulse nature of the high PIMS, the deposition rate of the high PIMS sputtering is lower than for the DC. In our case, it was about 50%. It was about 50%. But the energy flux in the high PIMS rate is 70% of the DC. Here, this is 70% of the DC flux here. So, and that means if you divide this by each other, then you get 140% energy per deposited particle. So per deposited particle is the incoming energy or the deposited power higher per particle than in the DC case. Not in an average, but per particle. And that means this is one reason why the thin film in high PIMS is much more dense and much more homogeneous and a larger grain size. This is related to these factors. And if we change the bias voltage of our probe, then of course here is the floating potential. There you have the lowest energy influx. And if you increase a negative bias potential, then it increases. Of course, you increase the energy of the ions, of the positive ions. And so the energy influx increases. And here on the positive branch at mass potential or positive, there is a steep increase in energy influx. This is due to the electron flux, the deposition of, or the flux of the electrons from the plasma. So it is a kind of an additional electrode now, which is a steep heating. The red curve is the experimentally measured curve, and the black curve is the model. And in our model, we took into consideration the kinetic energy of the ions, of the electrons, the recombination of the charge carriers, and also the secondary electrons. But you can see there's a difference between the model and the experiment. And this is because due to the film growth. There's a growing film, and so you have condensation energy, and this is the difference. And the condensation energy is almost not influenced by the bias voltage, of course. The bias voltage and the radiation and deposition, condensation energy. This is not so influenced by the ions. Another example is PIII, plasma ion immersion implantation. And this is, you have here your substrate. It's a cathode of a glow discharge. There is a glow discharge surrounding. In this case, the discharge was generated by an ECR, plasma source. And far away, we put our probe. So we could move the probe and we could circle the probe to measure the angle distribution. And as you know, during PIII, you have a short, very high negative pulse. And that means for a short time, you have a matrix sheath in front of the substrate. All electrons are depleted, and the ions are more inert than the electrons, so they stay for a certain time in the sheath, and then they are accelerated into by the high pulse, negative pulse, into the sheath or into the substrate, and so they are implanted, for instance, nitrogen ions. This is the principle of the plasma ion immersion implantation, and we measured here with our thermal probe, for instance, the angular distribution of the energy, and that's clear. 0 means it is phase to phase, and 180 means it is the opposite direction. So in the opposite direction, we don't measure any energy influx, and we measure the maximum energy influx at 0 angle. It's clear. And if you increase the pulse voltage or the frequency of our pulse, then also we increase the energy influx that you would also expect. But what is more interesting is that we can really measure by this method the secondary electron emission. So you can imagine if you pulse your substrate and the ions are accelerated to the substrate, then a high percentage of secondary electrons is released, and these secondary electrons are accelerated far away from the substrate, and they hit also our probe, these high energetic secondary electrons. And that we can see here. For instance, if we use magnesium, an oxidized magnesium substrate for the PIII, then at the beginning, so the first 10 to 15 minutes, there was a degree or about 90 milliwatt per square centimeter. But then suddenly there is a decrease in the energy flux to about only 10 milliwatt per square centimeter. And this is why during the sputtering, the substrate is cleaned. And so we have here an oxidized mode, and here we have the metallic mode. And of course, in an oxidized mode, the secondary electron emission is much higher than in a metallic mode. And that we can really see in the energy influx. So it's a very simple method, but you can get this information. And a certain example is ion beam sources. So we make optimization and diagnostics for ion beam sources, for instance, for these space thrusters for electric propulsion, but also for the surface modification. So it's a plasma, and there's a grid system, and the ions are accelerated through the grid system. I skipped the videos, and here you can see, here's our ion beam source with a microwave antenna. So it's an ECR plasma here. It's a torus-shaped plasma, and there's a grid system where the ions are accelerated. And here we have our substrate or our probe, our thermal probe. And we can change a lot of parameters. For instance, we can change the beam voltage, we can change the pressure between source and probe, we can change the distance between source and probe, and we can give an additional substrate voltage, or we can change microwave power, incoupled microwave power, or we can change gas flow, for instance. So here is the substrate which is treated by the ion beam, and we measured at the position of the substrate the energy influx. And of course, what you expect, if we increase the beam voltage, we increase the kinetic energy of the ions, of the extracted ions, and so the energy influx is increasing. This is clear, but also if we give an additional bias voltage to our probe, then if it is a floating probe, this is the magenta color, it's the lowest value compared to this blue value, which is minus 100 volts. So there is an additional kinetic energy due to the bias of our probe. And then we measured the radial profile of this ion beam, and the diameter of this ion beam, it's about 12 centimeters, and this is the center of the beam. And for an ideal ion beam source, you would expect a rectangular profile, but this is a real source, not an ideal. So this is the the radial profile measured by our thermal probe, as you can see here. And then if you would assume that only ions are coming from the source, then you can just calculate the energy influx just by multiplying the energy, which is given by the beam voltage, and the flux density. The flux density can be measured by a Faraday cup, and the energy we know by the beam voltage. And if we multiply this, we get these radial profiles. And these radial profiles are by a factor of 2 or 3 smaller than the measured by our thermal probe. And why? And this is just simple because in our chamber, the background pressure is not very low. There is a background pressure of a Pascal or something like that. And that means we have charge exchange collisions near the ion beam source. We have only ions. But far away, we have only fast neutrals due to the charge exchange collisions. And this is the axial profile from the ion beam source. And that means the ions, they decrease, but the neutrals, they increase by charge exchange collisions. And at the end, both contribute to the heating of our probe, both the ions and the neutrals. And that means our probe is the advantage is you can also measure neutral particles, fast neutral particles, for instance, by our probe. Here we measured the ion current, the axial ion current profile by the Faraday cup, and you can really see this is this profile. It's really by the ions. But if we measure with our thermal probe, the power density, then we get such a profile. And this is the profile of both, of the ions and the electrons. So this is really a very nice method. And so this brings me now to the other topic. We thought, can we measure not only the energy influx, but also the momentum flux? And if we put such a cantilever in the target, in the ion beam, then we measured also a force by this cantilever, and this force has the same profile than the energy flux. And of course, this force is also generated, or the momentum transfer is generated by ions and neutrals, and the fast recharged neutrals. So that we could also see in a very nice experiment. So we drop here's the ion beam source, and the ion beam is upwards directed, vertically upwards directed. And we have here the camera and the dust dropper. So we inject small dust particles in the beam, and we illuminate them and observe the particles. And maybe we can show now the video number 3, I guess. Sorry. Could you show the video number 3? Yeah, this one. You can see here, this is the this is the dust dropper, and here you can see trajectories of the falling dust particles. I hope you can see that. They are stroboscopically illuminated, and you can see these particles. Okay, you can go back. Okay, and if there is no plasma, then the particles would fall down, and due to Galileo's law, they are accelerated. And if we have an ion beam against the falling particles, then the particles are accelerated, they are decelerated, they stop, and they are accelerated back by the ion beam. And this is just the experiment what we did, and we could calculate these transferred force by the particles to the dust particles, to the probe particles, and we could compare these are the triangles, with our calculations of the power measurements when we include the ions and the neutrals. Here for the red circles, only the ions are taken into account, and it doesn't fit. So we have to take into account also the neutral particles. So that brings me to the next part, to the momentum transfer measurement. I explained the energy flux measurements, and now I explain the measurement of the momentum transfer. And the idea is simple. If you have sputtering, for instance, this is the target, there is an ion, incoming ion for sputtering, and there might be a sputtered atom or another sputtered atom, and there might be also reflected ions. And that means you have an incoming momentum and you have an outgoing momentum. And you can calculate these or simulate these processes by simulation codes for sputtering, like SWIM or TRIM or TWEEDLE. And the question is, what about the energy of the reflected particles? What about the angular distribution? And what about the momentum transfer? And we want to check these models, to check these simulations. And the idea is here very simple. If we have here our target and we have here our incident ion for sputtering, then we have maybe copper. We have sputtering of copper and reflection of argon ions. And if the target would not be fixed, let us assume it is not fixed, then due to this outgoing momentum, there might be a movement into this direction of the target. There should be a momentum conservation, of course. But if we fix our target in this direction, in the vertical direction, it can only move in the horizontal direction due to the horizontal part of this outgoing momentum, which is the same amount of this here, of course. Yeah, this is the simple idea. And then there was a nice masterpiece. We have in Christmas time in Germany, we use that, for instance, by the flux of the gas, of the air, this wheel starts to rotate, yeah, due to the reflection of the hot air. There's a convection of the hot air, and there's reflection, and due to the momentum transfer, it rotates. And that was the basic idea for our experiment. So there was a master thesis. He constructed such a wheel. The pedals are the targets. You can change the angle, you can change the material, and the rotation of this wheel can be measured just by a laser diode. This is the idea. And now, please, could you show the other video? Yeah, here you can see this is the plasma is here somewhere at the bottom. And now we switch on the beam. The ion beam is switched off, and really this wheel, the pedals, they start to rotate. This is a real image, a real-time image. So they start, now we switch off the beam, and it's decelerated. As you can, it becomes slower now again. This is a very nice experiment and a very simple experiment. Okay, we can go back. Sorry. Yeah, okay. So this is the acceleration of the wheel. This is the deceleration of the wheel, just measured by the laser diode. And if we plot this, then we get a perfect curve, as you would expect in mechanics in the first year in the textbook. This is the angular acceleration when the ion beam is on. And this is the angular deceleration if the ion beam is off. And we can measure very accurately the angular acceleration and deceleration. And if we know the torsional moments of our wheel, of our instrument, we call it spin. It is sputter-propelled instrument, we called it. And then we just know this. We know the moment of inertia of this instrument. We measure the angular acceleration here. Then we get the torsional moments. And so by this difference, we get the force which drives this wheel. And this is just by the sputtered and the reflected particles. It is not due to the incident ions, because that would work in the horizontal, vertical direction. But this works in the horizontal direction. This is due to the sputtered and reflected particles. So the movie, what you have seen, the rotation is just due to the sputtering and reflection of particles at the targets. This is I like this very much, a very nice experiment. And we could change in this experiment, again, different parameters. For instance, the distance between this instrument and the ion beam source. We could change the angle of the wheel, of the pedals. We could change the gas. We could change the material of the target. We could change the ion energy. So, and if we do that, then we measure the force. That means the momentum transfer. And as you would expect, again, if you increase, for instance, if you increase the beam voltage, then you increase the transferred force. Of course, this is here for a copper target and for argon ions. And the black points are the measurement, and the red points are the simulation with this trim code. And you see there's a difference between the measurement and the simulation. And why? This is because in the simulation, only the ions are included, but in our measurement, again, we have both. We have ions and fast neutrals. The rotation is due to the ion ion effect and the effect of the fast neutrals. So, and then if we take this into consideration, there's a good agreement between the measurement and the simulation. So we can do that for different gases, for argon, neon, krypton ions, and for different target materials, for instance, for copper and for graphite. And the force is much lower for graphite than for copper. And of course, the sputtering yield for argon ions is much lower for a carbon, for a graphite target, than for a copper target. That you can really see in this rotation, and you can measure that. And by comparing this, you can get information about the sputtering plume and the reflection plume of the particles coming from the target. And now I come to the last example. So we could really compare our measurements here, the measured force with our spin, with the calculated or simulated force by the trim, just by measuring this angular acceleration, and by measuring and knowing the moment of inertia of our instrument. And that brings me to the last example. Such a wheel is very nice and interesting, but you cannot use it in an industrial plasma or a sputtering environment. So we used another one. We used a cantilever, which is bent. And this bending is very sensitive. For instance, here is ion beam off, here is ion beam on. Then there is a bending of the cantilever, and this bending is measured by an interferometer. So we can really measure the bending of a few nanometers, and that means we can measure forces to our probe here in the piconewton regime, in the piconewton. So we can really measure the force of the ions and the neutrals. And this was originally interesting, again, for the space propulsion to determine the thrust, the small thrust for these clusters. So this is how it was constructed. There is still an eddy current damping, so that there is not too much oscillations, and we can determine the momentum. So we have here our plasma chamber. Here's the ion beam source, and here on the stage we have our instrument, the cantilever, and we can measure. We have two laser diodes to measure the interferometric signals into two directions. So we have an angular resolved force, so we can measure the force in the both directions. Yeah, if it is just perpendicular, then it's simple, but the ion beam could be under a certain angle, and then we measure the two components of the force here. As you can see here, here is one component, here's the other component, and the vector of the force can be distributed into these components, and they are measured by the interferometers. And so we measure this for different sputtering. And for instance, if you hear sputtering of copper at 2200 eV, Here are the angle of the incoming ions, and here the angle of our cantilever of the force. And if all incoming ions would stick at the substrate or at the probe, then we would have this line. Yeah, but the measurement is below this line, as you can see. And why? Because there is sputtering. There is an additional loss of momentum due to sputtering. So that means if all particles stick, then we have a momentum transfer of 1. If all particles would be reflected, then we have a momentum transfer factor of 2. So in reality, it is in between. Due to sputtering and reflection, we have a factor in between. And this can be determined very accurately for the different materials. For instance, as you can see here, we have several materials, different metals, and carbon. And this is a carbon fiber velvet where all particles stick. And you can see this is almost to this line. That means there's no sputtering and no reflection. All incoming ions or fast particles stick into this material. But if we use silver or copper, then we have a lot of reflection and sputtering, and we have a strong deviation from this line. And by this, we can calculate the sputtering effect or the reflection effect of the ions. This is important, for instance, to know this angular distribution if you want to sputter special structures like ripple structures or chevron-like structures if you rotate your substrate. Okay, and this is the last slide, I guess, or almost. Then we still go a step further. With this experiment, we measured the sputtering at the target. And now we measure not only the sputtering here at the target, but we measure the deposition of the sputtered particles from the target to the substrate. Now our scanning force probe is the substrate. It is not the target as before. Now it is the substrate. So we have here our ion beam, as you can see here. And here we can rotate our probe surrounding the target and measure the incoming force. And here you can see this is the scanner angle. That means the angle of our force probe surrounding the target. This is the substrate. And alpha is the angle of the incoming ion beam to the target. And as you can see here, for instance, we have here an angle of 45 degrees of the target to the ions. And if we are larger than 45 degrees, then we have a very high force. And this is clear. Then we measure the primary ions. Then the primary ions from the beam are going to our probe. But if the angle is lower than 45 degrees, then we just measure not the primary ions, but we measure here the sputtered particles from the target. And this is a quite good agreement. Here it's for different acceleration voltages or beam voltage. In a good agreement, the measurements with the simulation. So you really can check and here it is for changing the angle of our probe. Also we can, and from that you can get information about the sputtering mechanisms, and you can compare the measurements with the sputtering models. Okay, I'm coming to the end with my summary, and I would say that, of course, if you want to change surfaces, if you want to deposit in films by sputtering or by PECVD, you have to know something about the plasma process. You have to diagnose the plasma process for optimization. And in addition to the common diagnostics, we need, or it is important to have some non-conventional diagnostics like these calorimetric or thermal probes, or like these force probes. They are rather simple, and you can get a lot of information, especially also on neutral particles, on the flux of the neutral particles. But of course, this can only be a supplement in addition to the common diagnostics, Langmuir probes and spectroscopy and so on. But it can be very helpful to get more insight, to get more information about the plasma surface interaction. Okay, thank you very much for your attention.
Thank you very much for your excellent presentation. Any questions, please? For question, please use chat. During your presentation, you talked about xenon ions. Where these ions used in your experiments?
Yeah, this was just an example. The xenon ions were used in an example for the space thruster, for the ion, for the electric propulsion. As you know, in these electric propulsion ion sources, they use xenon ions because they are very heavy. They have a high charge to mass ratio if they are accelerated, and so we just checked also this. Our probes in this xenon plasma. The background was the electric propulsion. It is not for surface modification or for thin film modification. It was for the electric propulsion.
If compare argon and xenon to obtaining homogeneous excitation, more easy in argon, of course.
Yes.
Yes.
Yes. That's true. Yeah, we also used other rare gases like krypton and neon, and especially for krypton and neon, it's more difficult to have a homogeneous plasma than for the argon plasma. Yeah.
Okay. Any questions? I see. Please look question. Do you see at the beginning of you talk about carbon structures?
Yeah.
I am interested why nickel dopes were used in food repellent for carbon structures.
Yeah. Yeah. This is just was used. You know, if you want to grow, for instance, carbon nanotubes in an acetylene or methane plasma, you need a kind of a catalyst of a footprint. Often iron is taken, but also nickel can be taken as a catalyst at the substrate where the carbon nanotubes are growing on this catalyst, on the nickel in this case. And we use that also for the growth of our carbonaceous, of our carbon structures, of our carbon pillars. So it is just a catalyst where the structures start to grow.
More questions? Okay, thank you very much again for your presentation. I hope in future you will visit Tomsk and our Congress. Thank you very much.
I hope too. Thank you very much. До свидания.
The session is closed.